In this video, what I would like for us to do is revisit recent results, actually going all the way back to our starting axioms that we covered in lecture 2, and see how we built up to our most recent result, which was Bolzano-Weierstrass. So that's what we will do, is take a tour of recent results that led to Bolzano-Weierstrass, and then I would also like to present a few other ways to order results and even a different axiomatic structure. So first, starting with the axioms, I've separated them into two boxes up here at the top. On the right is the supremum property. That was what I called our completeness axiom, and it said that every set of real numbers which is bounded above must have a least upper bound, or in other words, a supremum. On the left, I'm putting the ordered field axioms. That told us that addition, multiplication, ordering of real numbers behaves the way that we expect it to. So we have a way of combining numbers, which makes sense, and also we have a way of ordering them. In all of the charts I'm about to put up, you'll notice that this box basically feeds into everything because all of our machinery that we've built up, algebra, inequalities, but also notions like boundedness, our ability to create intervals, create estimates, compute limits, define convergence, that all goes back to just having an ordered field. Okay, so traveling back in time, I think the first result we need to cite in order to get to Bolzano-Weierstrass was in lecture 5 when we had the criterion for sups and imps. That gave us another way of characterizing what it meant to say that something was a set supremum. We used that in order to develop the Monotone Convergence Theorem in lecture 18, so the MCT. A few lectures later, we met a similar sounding result, the Monotone Subsequence Theorem, or MST, and you'll notice here that actually I'm saying that just follows directly from the ordered field axioms. If you revisit how we proved the MST, we had that proof where we created like a family of peaks, and all that really needed us to be able to do was write down inequalities. Then with the MCT and the MST, we gave our first proof of Bolzano-Weierstrass. It was a very short proof with just a couple sentences, so I will call that short proof number 1. So here's one possible route to Bolzano-Weierstrass. But of course, we've done a lot more in this course, so let me mention an alternative path. When we defined Cauchy sequences, all we needed was the ordered field axioms. That was just a definition. And similarly, when we proved two results about Cauchy sequences, that they are bounded, and that if a Cauchy sequence has a convergent subsequence, the Cauchy sequence itself is convergent, those proofs just needed us to be able to construct a bound and use the triangle inequality. So that comes straight out of our ability to compute on R. But with those two results, the MCT and the MST, we built up the Cauchy completeness of the set of real numbers. That's a major statement, and it tells us that every Cauchy sequence of real numbers is convergent. The converse is also true, but that's always true. So every convergent sequence is always Cauchy. And then in lecture 24, we did a second proof of Bolzano-Weierstrass using Cauchy completeness. It was a much longer proof. It was constructive. What we did was we enclosed our bounded sequence into an interval that we subdivided into 2 in order to construct a Cauchy sequence. And then we said, hey, that Cauchy sequence converges because of the completeness of real numbers. So that was our second proof of Bolzano-Weierstrass. And as I wrapped that proof up, I mentioned that you may have spotted another way to get to Bolzano-Weierstrass, and let me put that explicitly on this diagram. Going all the way back to lecture 6, when we were talking about sets of real numbers, we proved the nested interval property, and we used the supremum property to prove that. In addition to the nested interval property, we had a second version of it that told us that if you have a nested family of closed bounded intervals and their widths are shrinking to 0, there's something that lives in the intersection of all of those sets, and in fact, that element is unique. Then if you revisit that constructive proof of Bolzano-Weierstrass, you recognize that what we are creating is a family of nested closed bounded intervals. And you could do almost the exact same proof, but have a different conclusion at the end, where the subsequence you build up, instead of showing that it's Cauchy, you show that it converges and its limit is that unique intersection point. To summarize, these are the 3 paths that I think are most natural in this course to start from the axioms back in lecture 2 and arrive at Bolzano-Weierstrass in lecture 24. Both versions of proof number 2 are optional because we have that short proof number 1. You don't really need to prove Bolzano-Weierstrass 3 times. So if I wanted to reorganize this, I feel like this chart takes us from the axioms to 2 large results that we recently proved, Bolzano-Weierstrass on the left and the Cauchy completeness of real numbers, that all Cauchy sequences converge on the right. And here I'm removing optional extra proofs. So this was how I chose to present the material. I did it this way because I like the proofs that emerge. I really like combining the MST and the MCT to get both of the major results at the bottom. with the monotone subsequence theorem and the monotone convergence theorem, proving both Bolzano-Weierstrass and Cauchy completeness, it turns out to be very short. So I think that those proofs are simple and elegant. But not every path through real analysis follows this train of thought. So I'd like to show you a couple of other different approaches. So here's a fairly common approach. I'm just going to take all of the same results, but reorder them in a way which is still rigorous and correct. In this approach, we will have the same starting axioms. So our ability to work with R as an ordered field, and then also the supremum property. Let me immediately mention that the monotone subsequence theorem and those initial results we had about Cauchy sequences, they follow right out of our ability to do algebra. And what you'll notice for the rest of this presentation is that we're not going to use the MST anymore. So I'm going to leave lecture 21 off to the side. Okay, what does this path look like? Well, it starts the same way as our course. So from our starting axioms fairly early on, you would develop the criterion for sups and imps. And then again, following the order of topics that we did, from there, you could prove the nested interval property, the exact same way that we did. But now consider this variation. So here's where we're going to have a change. If we did that alternative proof number 2 from the nested interval property, where we said, okay, let's take our bounded sequence in the hypothesis of Bolzano-Weierstrass, enclose it in an interval, and then start chopping intervals in half to create a nested family of closed bounded intervals, we could just prove Bolzano-Weierstrass directly. Here, there's no mention of Cauchy sequences, there's no MST, there's no MCT. You can see we get to Bolzano-Weierstrass a lot faster. Now, in a major reversal of the ordering from our course, with Bolzano-Weierstrass, we could prove the monotone convergence theorem. Let me do the first half out loud, and I'll leave the rest of it to you as an exercise. So let's think of how we would prove the MCT as a consequence of Bolzano-Weierstrass. In the hypothesis of the monotone convergence theorem, we have a bounded monotone sequence. Let's imagine it's monotone increasing. Since it's bounded, it's a bounded sequence. Bolzano-Weierstrass tells us that it has a convergent subsequence. So now we can say there's a real number out there that we could identify as the limit of a subsequence of our bounded monotone sequence. So then here's what I want you to do. Fix epsilon greater than 0. Since a subsequence converges to some limit L, there's a threshold out there beyond which all subsequence terms are within distance epsilon of the limit. Can you use monotonicity to argue that actually all sequence terms beyond that threshold are also within distance epsilon of the limit? If you can, then you prove that the overall sequence also converges to the same limit. So the MCT could be shown as a corollary of Bolzano-Weierstrass. Similarly, we can show from Bolzano-Weierstrass and our pre-established facts about Cauchy sequences that Cauchy sequences of real numbers must converge. And this implication is actually very fast. Imagine that you have a Cauchy sequence of real numbers. Well, we know it's bounded. So by Bolzano-Weierstrass, we know it has a convergent subsequence, which means that the overall sequence must also converge to the same limit. There I'm using both of the results over on the left. This path does not use the MST, which I enjoy using, but I do think that this is a very nice, clean path through the results. And I think it is a fairly common approach to show Bolzano-Weierstrass at least before Cauchy completeness. However, I think the MCT is such a useful tool. For example, we used it with recursive sequence limits, and it just comes up sometimes, that I would rather introduce it earlier than this path might lead me to do. So that's why I have the monotone convergence theorem coming in before Bolzano-Weierstrass. Okay, now let's look at a kind of radically different arrangement of real analysis. You'll notice in this diagram that I've moved the supremum property down and Cauchy completeness up. That's because I'm going to switch their roles. Another axiomatic structure for the real numbers keeps the ordered field axioms, but says, let's call the completeness property the Cauchy Criterion. So instead of the supremum property, your third axiom would be that every Cauchy sequence of real numbers converges. I think that for an analyst, this is a very sophisticated way to think about the real numbers, but you can see why it's not often done in the classroom in a first semester analysis course, because you would have to spend the first day of class talking about Cauchy sequences, and I just don't think that that's very practical. So while in some ways talking about the completeness of R by saying R is complete, Cauchy sequence converges, feels correct, it's hard to actually do that in the classroom. Okay, but let's walk through the material with this ordering. Once again, I might as well just go ahead and connect from the ordered field axioms to the two results on here that really need no other results. And then just like before, the monotone subsequence theorem, we'll leave that to the side. Now again, it's a hard thing to actually imagine implementing in the classroom, but day number 2 of real analysis could be to show that if Cauchy sequences of real numbers converge, then you get the Bolzano-Weierstrass theorem. And that is just the proof number 2 that we already did, where again you enclose your bounded sequence in an interval, subdivide, subdivide, build up a Cauchy sequence, which you know to converge by Cauchy completeness. So it's the same proof that we already did, but it would come much earlier in the course. And if Cauchy completeness and Bolzano-Weierstrass were all I really cared about, we would be done with this chart, but let's go through the rest of the results here. From Cauchy completeness, the fact that all Cauchy sequences of real numbers converge, you can actually prove the nested interval property. Previously, we proved that using the supremum property. Here, as you nest your intervals, you would construct a Cauchy sequence at the same time. And then your Cauchy sequence must have a limit, and you can show that that limit must live in all of the intervals. So that's how you get to the nested interval property. Again, I'm just doing that out loud, but feel free to try to prove that as an exercise. I think it's a good thing to do, to take any of the arrows on this chart and see if you can do the proof. And then again, the radical shift in this diagram is that the supremum property is no longer an axiom, it's a consequence. So here you imagine that you have a set of real numbers which is bounded above, and you prove that it must have a least upper bound based on, say, the nested interval property. And to do this, I'm not sure I can explain this very well out loud, but basically you nest intervals where the left side is not an upper bound and the right side is an upper bound, and you drive them to a unique intersection point, which turns out to be the supremum of your bounded set. And then as we did in the past, same proof as before, from that you get the criterion for sups and imps, and then from that you could get the monotone convergence theorem. And then for this axiomatic structure, you could also come up with other alternative paths. For example, instead of proving Bolzano-Weierstrass on day 2 as a consequence of the Cauchy completeness of real numbers, you could do the same proof that we've already done together and show that Bolzano-Weierstrass follows with a combination of the MST and the MCT. Same proof as before. Similarly, you could take alternative proof number 2 and build up Bolzano-Weierstrass from the nested interval property. I think in this chart that's a little bit silly compared to going directly from Cauchy completeness, but it would work. And as we've already discussed, there's also a major rearrangement you could do here with the Bolzano-Weierstrass and the monotone convergence theorem. Perhaps we start with the same initial configuration. We could rearrange how we prove the Bolzano-Weierstrass theorem and the monotone convergence theorem to show the monotone convergence theorem as a consequence of Bolzano-Weierstrass. So in all of these configurations, there are some variations which are possible so long as your proofs are not circular. So whether you follow this train of thought or the course as I presented it, what's always essential with real analysis is to make sure that you are correctly building up your results based only on the prior results which you have already proved. I hope this video gave you a few different good viewpoints of this material. Again, I think it's a really great exercise to take any of these diagrams and practice going from one box to the next. So can you, for example, prove Bolzano-Weierstrass again as a consequence of the monotone sequence theorem and the monotone convergence theorem? Or as another exercise, can you prove how the monotone convergence theorem can be shown following the criterion for sups and imps? There are lots of exercises that you could come up with. Thank you for your attention.